let's just make a quick start. So we're going to create a Linux server in this lab. Some of you have already done this before. The big difference is, because it's headless, we have to do things like give it static IP addresses, we have to configure it so we can find it on the network. And I'm going to show you everything you need to get this done. So this is what we're going to cover this week and the first half of next week's session. We're going to look at configuring Linux, installing Linux on your SD card. We're going to cover some networking. We're going to look at how we resize partitions, because I'm going to give you a 1 gig image. If you put that 1 gig image on a 16 gig SD card, it will ignore 15 gig of space. So we need to resize the partition to maximise the space we've got. We'll look at how we install software. We'll look at access control, the words owners, groups, permissions, and so on. And finally, we'll look at how we do account creation. So we're going to cover quite a lot in this first session. Right, so we've got a lot to cover. So let's start. Now, Raspberry Pi. Okay, all it is, it's a small ARM-based computer. It's the same chip you find in some of the older smartphones. So it's an ARM 6 processor on there. It's system on chip. It's got a fantastic graphics card. So if you get bored doing servers, you can create a media center with it. And it's a good idea to get yourself one of these so you can carry on with labs at home. If you're thinking of doing extension tasks, the higher grade, it's almost essential you get one of these, unless you want to come to all 3 lab sessions each week. Things you must bring next week. You must bring an SD card, well this week, tomorrow isn't it for some of you, the lab. You must bring an SD card of at least 2 gig, 4 gigs perfect, and you must bring yourself a micro USB cable, because that's how we power it. We're going to plug it into the desktop computer in the lab and power the Raspberry Pi. It takes about 2.5 watts of power, so it's a really low power device. I've got a couple of micro SD cables, micro USB cables around, but not many. So if you bring a micro USB cable, you'll save yourself a lot of time. Other useful kit, which you might want to buy, if you're going to be doing work at home, you shouldn't have to plug it into a TV or monitor, but you may have to debug it. So it's always a good idea to have an HDMI cable or an HDMI DVI cable, so you can plug it in at home and carry on with the work. And also, you're going to be installing images on your SD card, so make sure you've got access to an SD card reader and writer. Otherwise, you won't be able to install the operating system. So that's what you should need. There's one other piece of kit which, from bitter experience, you really should have with you at all times. A notebook. You're going to be learning dozens and dozens of new commands, and each command will have different option flags. It'll do different things. You have to create configuration files. It's always a good idea, as you learn new skills and find new commands, you make a note of them. That's what I do in a book. You know, what they do and how they work, dated, so when I get stuck later on, I can flick back through my pages and I can find what I'm looking for. I will try and include as much information as possible in the slides, but keep a record of what you've learnt. I've got several of these books all stacked up by the computer at home, going back years, with all the commands I've learnt and the options and the configuration files and so on. Right, you're going to be working in pairs in the lab. The reason we're working in pairs is I think you'll get more out of it, not because we're stingy when it comes to Raspberry Pis. We have almost enough Pis for everybody in the labs, but I still think working in pairs is better. Make sure you have your SD card for your pair. Make sure you know who you're working with before you come to the session so you can get straight into it. And if you want to work on the assignment, the extension task, you're going to need to buy your own. They are quite expensive, aren't they? Go on. About £30 all in, including postage. Yeah. So they're worth having. You probably get them cheaper on eBay as well. And I'll probably wait for everyone else to buy them on eBay first. The prices suddenly went up. As soon as I mentioned the assignment, I was monitoring eBay prices, and the average price for a Pi went up by £8. Within days of me launching this assignment. Right, Linux distributions. Right, Linux. It's just an operating system, just like Windows. So you probably covered it in 2. Did you operate systems last year? Okay, which I guess you haven't. It's a Unix-like operating system, which basically means the history of this operating system goes back 40 years. Unix was the first cross-platform operating system in the 1960s and 70s. The big thing about it is it's completely free and open source. So you can download it for free, use it for free, you've got the source code so you can change it and modify it if you want to. So if you're doing 389, you could use Linux as your assignment. Download it, submit some bug fixes and so on. The user interface is called the shell. So when I talk about shell scripting in Lab 6, in week 6, I'm talking about scripting commands to work in the interface. There's two interfaces, command line interface, in other words, like you connect to with a secure shell, PuTTY, and graphical interface. We're going to use the command line interface for everything. So that's why the whole operating system and storage fits on 1 gig. There's another version of Linux called an embedded version. And if you've got a camera or a smartphone or a GPS unit or a car, you've probably got embedded Linux running your device. So it's for every Windows computer, there's 10 Linux devices out there. So it's the most popular operating system on the planet. Now, you've come across the term Linux distros. Okay, it's kind of one of those kind of acronyms, one of those little sort of geeky terms you come across. All it is, a distro is the core Linux operating system with extra software added. And because it's free, anyone can create their own distribution. They can download Linux, they can compile Linux for their platform, they can add extra packages in, and then bundle it up and stick it on the internet. So there are hundreds of Linux distributions. But most of them are designed for Intel architecture, Intel processors. There's about 6 for Raspberry Pi ARM processors. So there's still quite a few to choose from. If you're getting going with it, one is called Noobs, which is basically 5 operating systems on the same image. When you boot up, you can switch between them to try them out. But we're not using that. We're going to use a server distro, a server bundle of Linux. And what's special about the server bundle is there's no graphical interface, so it's completely command line only, and it comes with almost nothing installed. I think it comes with secure shell, and that's it. There is literally nothing else on that image, which basically means you can connect to it using secure shell because that's already been installed, and after that you can do whatever you want to it. Install whatever you fancy on top of that. So that's why we're going to be using the server version. And the idea is, every time you run some software, you're running background processes. And if you're building a server to serve lots of people, you want to reduce those background processes. You want to just install the bare minimum to get through. The image we're going to use is based on Debian Linux, which is one of my favourite versions of Linux. I use Debian whenever I build a server. The creative server is built on Debian. And Minibian is basically Debian compiled for the Raspberry Pi. So the operating system you're using is virtually identical, in fact is identical, to the operating system installed on the creative server. So anything you see on the creative server, you should be able to achieve using this operating system. So obviously you need to download that, and it's about a 300 meg image when it's zipped up. So it's tiny. Yeah, a whole operating system in 300 meg. That's one reason I like it. And it's really simple, 4-step process to install the operating system. You download the image, you install it on the SD card, you shove the SD card into the Raspberry Pi, and you switch it on. That's it. And if it all goes wrong, you simply take the SD card out, stick it on again, shove it back in again. It takes about 10 minutes for the whole process to download, install, and run the operating system. So it's really quick. If you're worried about it, I'll show you how you can back up your operating system back to an image. So if you get to a stage and everything's working, say between each of these steps in the assignment, you can back it up and make a whole backup copy of your computer. Now, the easiest way is this website here, elinux.org, and they have instructions for Mac, Windows, Linux and so on. There's a graphical tool. The Mac is called RPI SD card reader, and in Windows you use Win32 disk imager. They're both free, and I would strongly recommend you get this thing installed before you come to the lab session. so you can have a go at this. Then if you have problems, we can help you out. And there's also command line tools. This is how I get the image on the card. If you're on Linux or Windows, there's a built-in command called DD, which is a disk imager, and that's the command to install on the SD card, and that's the command to back up. And it looks complicated, but think about when you can script this. You can put it inside a Python script now, and just run the whole thing automatically. In fact, the Mac application on the previous slide is built on top of this. There you are, right. So that's the block size, that's the image, and that's the destination. You see, look, image is the image file, destination is the partition, is the SD card on the computer. This one, the origin, is the starting point, the source is the SD card, and the destination is my backup image file. So if you look at it that way, it's actually the same. It's very simple, isn't it? The block size, where the file's coming from, or where you want to save it to, and that's it. So if you're on Mac or Linux, this is the recommended way of doing things. It's a lot quicker as well. Now, it takes about 10 minutes to install the image, but obviously you've got to have the software has to be installed on the computer. You have to know what you're doing. There's a lot of faffing around. You could lose an hour's lab time trying to get the image installed. So please, could you have a go at installing the image before you come? You haven't got to have a Raspberry Pi, remember? All you have to have is the SD card and download the image. If there's an error, obviously you know it hasn't worked. If there's no error, it means you can literally bring the SD card in, plug it into one of our Pis, and you can do the lab task. So bring your SD card with Minibian pre-installed on it, please. And then what I'll do, I'll bring my laptop, and you'll bring his laptop, and Abba will bring his laptop to the session. So if you have any problems with it, we can help you out and reinstall the image. But we don't want to sort of queue snake into the door at the start of the lab session. And that's the Raspberry Pi. There's your, ignore that one, that's your old sort of TV connection. That's a 3.5mm headphone socket. That's the USB sockets. That's your network socket. There's your HDMI, and there's your micro USB power. That's it. The ones we've got have got cases on, so if you drop them or anything, it doesn't matter. But obviously, when you buy them, that's literally what you get. And this is there's pins here to connect motors, switches, connect external sensors to it. And basically, that's the graphics processor, and that's the main processor. That's all you get on it. When you install it, the important thing, which they don't tell you very clearly, is there's a root account on the mini Debian image. The username is always root for the root account. The password is set to Raspberry. Okay, so it's obviously you need to change that one pretty quickly. And technically, you never ever need to plug it into a monitor. You'll need to do when you first set it up to give it the IP address, but then that's it. The trouble is, because it's designed for HDMI TVs and high-res monitors, you switch it on and the fonts are like this, tiny little characters. So what you have to do, you have to squint to edit that file and add that line to that file. Reboot the Pi, and you get a nice chunky writing on the screen so you can see what you're doing. And if you want, there's about 40 different graphics modes on it, and that website there gives you all the graphic modes, all the options. That's a widescreen version of 800 by 600, if you want to know. So it's 600 tall, but it's a bit wider than 800 to fit the widescreen. Right, this is the important bit, networking. Now, when you're working in the labs, you will not be able to run on a static IP address properly because of all the security. So for the assignment, if you've got one at home, you can do the static IP at home and do the screenshot and do the notes from home. If you haven't got one and you want to do it here, do all the changes, boot it up, and just do some screenshots of it working. But they've been blocking some static IPs, and that's going to cause us a few issues. So you're going to have to run the lab session on DHCP, okay, dynamic IP address. Okay, normally you would have a static address, static IP, and if you plug your Raspberry Pi in at home, I'll show you how you create a static IP and how you configure it as a server at home. When it first boots up though, it's using DHCP, so the problem is you've got no idea what the IP address is. And that's why you need to plug it in to a monitor the first time you boot up. Just so you can grab the IP address of the system, that's all you need. Once you've got the IP address, remember you can secure shell to it, can't you? Yeah, you've got the IP, so the server name is the IP address, then you simply connect to that IP address, and then you log in as root. But that first time, it can be tricky, but I will show you how to get around that when you're at home. Now, most computers on your network are given DHCP, are given dynamic IP addresses. In other words, your router at home and our DHCP server here, the computer tries to log in, the server gives it an IP address, and then a couple of days later, it takes it away again and gives it a different one. So if you rely on DHCP all the time, you can't guarantee what the IP address is, even if you found out the first time, because it will change over time. And that's why giving it a static IP address is really important. And if you want it to become a proper web server, so you've got a domain name, you need to supply the domain name when you apply or you attach your domain name to it. So you need the IP address to connect to the domain name. Imagine if you had a domain name attached to an IP, then the IP changed every 72 hours. You spend your whole life reassigning the settings. So we're going to show you how to set the static IP address. Now, this is the secret, the sort of cheat, if you like, to getting your Raspberry Pi working at home. You're going to plug this into your router. Your router has 4 network sockets on the back, labelled 1, 2, 3 and 4. In other words, if you go to your settings page of your router and you know which port you plug that Raspberry Pi into, it even comes with Raspberry Pi, but even if the name doesn't come up, you know that that device is in that port, don't you? Does that make sense? If that device is in that port, all you've got to do is check the device settings connected to the port, and there's the IP address. So I never ever plug my Raspberry Pi into the TV ever. I'll just install the operating system, plug it into the router, check the settings, and then connect using secure shell. So you technically don't even need to have a graphics cable, a video cable for your Raspberry Pi. And you can see it's on DHCP and it's assigned in 192.168.178. So, the important thing next is your router is assigning IP addresses. What you do not want to do is give it a static IP address that might be accidentally reused by the DHCP server. Does that make sense? So every router will have a pool of IP addresses that it will be giving out to the devices. And see, this pool starts at 64 and ends at 253. It's critical you do not assign any static IPs in that range, because there's a risk that the router will assign that again to another device, and then you've got an address conflict on your network. So I just took one less than that, and when I set mine up at home, I used 63. It's outside the dynamic range, which means the router will never ever try and use that IP address and assign it to a different device. Now, if you're connecting to a business or university network, you'd actually contact the IT services team and ask for an IP address. And they will give you the IP address, because obviously they know what the range is on, what they've assigned already. And often they'll ask you for the MAC address. I'll show you the next slide or two. Can you see this physical address there? That is the MAC address. That's the address of the network card on the device. And every network card ever produced has a different address. It's like a serial number for the network port. And because they're all different, if the MAC address is supplied when you ask for the IP address, they can tie the IP address to that MAC address so no one else can nick the IP. So no one can spoof that IP. So often that's a security measure you'll be asked to support. Right, there's a problem. We have to supply 6 different IP addresses to configure our system. And they all do different things. This is going to be a big problem, isn't it? But we can cheat, again. Because the DHCP server has already picked those values up from the router. So all you've got to do is make sure you make a note of them before you change to static, and just use the same values again. So when you're on your Raspberry Pi, if you type in ifconfig, which is the network config settings, it gives you all this data. So it gives you the hardware address, the internet address, which is the address that's the IP address that's been assigned to, a broadcast address, a mask address, and if you use the netstat command, you get two more. You get a gateway and a destination address. You need all those values. The ones I put in red are the ones you need. So hardware is that's your MAC address. Okay, that's the if you need that. There's your IP address that is currently assigned. Broadcast, mask, gateway, and destination. And you literally run those commands and make a note of those values, copy and paste those values, and keep them somewhere safe. Because you'll need those when you come to configure your static IP. So let's quickly go through. The MAC address is the hardware ID for the network interface. The device IP is the IP address that's been assigned by DHCP. Okay, that's the one that's currently running on. The broadcast, if you transmit a message to the broadcast address, it gets sent to all the devices on the network. Okay, so these are sort of networking terms. The subnet mask separates the internal network from the external network. It's a mask, so it's a filter to separate the two networks. The gateway is the IP address of your router. Because your router will have an IP address on the network, because it's a computer. So you need that router address so it knows where to go to get an internet connection. And the destination address basically means use these settings for all the traffic. So those are the settings that you need. And the trick is you've got to connect from your Pi through the router to the internet. That's the challenge. And we're going to test the connection by pinging the Google server. So you say ping www.google.com, and if it comes back with some times, you know it's working. If it comes back with not found, you've messed up your settings somewhere. So what we're going to do, we've got to configure our network device, our network card on the Raspberry Pi. Now, one thing you need to understand is Linux is a file-based operating system. Everything is files. Even folders are files. Everything's a file. Now, when you configure something, there's no wizard, there's no box where you choose the options and you click OK. All configuration's done in text files, which sounds really primitive, doesn't it? A really basic way. You know, Windows, you've got these pop-up windows and all the options. It's actually much more powerful. First of all, if you're having problems with your configuration, and you've got Stack Overflow, for instance, or a website, you can simply copy the contents of your config file and paste it into the question. And everything's there to be seen. So everything. So basically, if you've got one working on one server and you want to have the same configuration on a different server, you simply save the file from the first server and load it onto the second server, or copy and paste the contents of the configuration file across. So it's a much better thought out way of building configuration into the systems. And the file is etc. network interfaces. That's the folder path. Etc. is all the config stuff. Network, you've got one for Apache, a folder for your database for MySQL, you've got a folder for the file system, file servers, you've got a folder for the FTP server. They're all in the etc. folder. And in there, that file's called interfaces. Unlike Windows, you tend to find a lot of files don't have file extensions. So that's the file name, but there's no file extension. It just loads. And that's what it looks like at the moment with DHCP. I've hidden a lot of the rubbish at the top. There's a section called Primary Network Interfaces, which is called ETH0, Ethernet 0. Remember, everything starts at 0. And allow hot plug, which basically means if you put a cable in after you've booted up, it'll trigger the network systems. DHCP, and that automatically configures it when you boot up. So that says configure when you boot, that says configure when you plug a cable in, and that says use a DHCP server, the IP address. So we're going to replace it with that. Now it looks a lot, but actually it's simply the values we've copied from the ifconfig and the netstat commands. First of all, look, we keep the auto ETH0 because we want it to configure when we switch on, don't we? We need a network connection. Now it's static instead of DHCP. So it won't look for a DHCP server. There's the IP address I want. There's a net mask. The destination address is called network in the configuration file. And everything else has exactly the same labels as in the ifconfig and netstat dumps. And you simply copy and paste those values in. And that's it. You now have a fully configured static IP address on your network. So it's not hard once you know the tricks. And when you've done that, you need to reboot your server. You could just restart the network, but I tend to reboot at this stage. Shut down. Okay. -R means reboot, and now means just do it. You can actually put a timestamp on there, and it will wait. So if you want to restart in 3 hours' time, you can say shut down -R and put 3 hours in there, and it will shut down in 3 hours. But these little things here are called flags. Okay? And a flag is an option, a parameter if you like. So when you restart it, it loads the config file because we said auto ETH0, didn't we? And you've now got your static IP address. And all you've got to do is check to make sure the settings are correct by using the same commands, and then just ping Google. And if you get a response, you know you've got an internet connection. If you get no response, rewind a few slides and start again. If it all goes horribly wrong, you can always go back to DHCP, can't you? And have rerun the process. And now you can connect using PuTTY, secure shell. So in a lab, you're going to work in pairs on those two computers. On one computer, you're going to log in as normal. On the other computer, you're going to plug the Raspberry Pi in. So you can secure shell from the left computer to the right computer, to the Raspberry Pi, and you've always got the stuff on the screen. So if something goes horribly wrong, or you need to get the IP address, which you will, you can see the IP address on the screen. That's another reason why we're going to work in pairs. So you've got both. You plug the keyboard, mouse and monitor into the Pi, you power it off the base unit, plug the power it up, and you should be able to access the server and the client at the same time. Just please remember to plug the cables back in when you've finished, otherwise I will be crucified if you don't do that. Then I will come and crucify you for not doing it, because I was crucified for not doing it. Yeah? So please make sure when you've finished you replug. You remember when the first years used the Pis in the room? Remember that horrible session? The first lab session on Wednesday? And we lost 40 minutes reconnecting the computers because they left all the cables loose. So, yeah, you know what it's like if you walk into a room with the stuff all loose. Now, this is something for you to do on your own laptops and your home computers. You know how you have to put the IP address to connect to the server? Yeah, you have to use the IP address for the host name. I don't. When I'm at home, I type in mtires@Raspberry Pi, and it connects to my server. And that's because there's a host file on the computer, on your client, and it lists all the server names on your network. So if you simply add an extra line to your host file, you can then connect at home using the name of your server. And all you do is add that line. Now that's your IP address, and that's whatever name you want to give your server. So it's just a convenience when you're at home to connect to your system, to give it a host name. But this is done on the client, not on the server. I'm not entirely sure you've got access to the host file on these computers here. Okay, we're doing okay. So I think this lecture will be about building a Pi and getting it ready to go. And we'll talk about installing software and the counts next week. Right, when you boot your machine up, the SD card comes up as this one, multimedia card block 0. So if you see that in your list of drives, list of partitions, that is your SD card. And it contains 2 partitions on the SD card. Unlike Windows where you've got a C drive, there are no drive letters on Linux. Simply everything maps off the root, which is the /. So slash etc slash hosts was literally the etc folder in the home folder. Now, Linux has two partitions. The first one is the boot partition, the second one is system. The boot is just all your stuff to get the system booted up and working. And the second system partition is where all your files are kept and the applications are stored. And you can see P1, partition 1 and partition 2. Remember that. That's really, really important. I'm going to give you a 1 gig image for your Raspberry Pi. Which means you have a 16 gig SD card, you install this partition, you only actually got 1 gig. It's wasting 15 gig on your SD card. Which is a bit of a waste, isn't it? What we need to do is we need to expand the partition. Now, your friend here is the df command. If you type in df, it displays the disk space on each. So you can see at this point, I had a 4 gig SD card, but the main root partition was only 783 meg. And as you can see, by the time I got to lab task 3, I had nothing left. So at this point I thought, right, I need to show you guys how to resize partitions. Can you see, there's the SD card, just there. /dev/mmcblk0. Now, and you can see here, look, available 0, usage 100. I'm out of space completely. So you can keep tabs. That's why we run out of space. That blue is my SD card. The red is my boot partition. And the orange is my root, my system partition. And there's all this space wasted in my partition. What we're going to try and do is we're going to expand this second partition to right to the end of the SD card. So we've maximised the space. And you're going to have to do all of this using Secure Shell. Everything you do on this server is command line interface. And this is why it's a good idea to keep a record of what you've done, keep a notebook, and whenever you work on servers, keep the notebook handy. I need to use an fdisk command. Disk formatter. This allows me to format partitions, resize partitions, and do all sorts of cool things. Now, I need to access the SD card. See that P1 at the end? That's the partition. I want the whole card. So I fdisk /dev/mmcblk0. So I fdisk the whole of the SD card. And when I've done that, I get this thing which says Command M for help. It's an interactive tool. It's like a wizard. It's the command line interface equivalent of a wizard that you go through step by step. So, let's go through the process. The first command I use is P. And P stands for partitions. And as you can see, I've got two partitions, partition 1, partition 2, which maps to those two. That one starts at 2048 in memory address and finishes 15.15.5647. The next partition starts at the next one. Can you see, look? So the next partition starts the block afterwards and finishes at 1,816,000 and so on. And uses 830,000 blocks. So that's what it currently looks like. Now, we're going to rebuild this second partition. If we're going to rebuild the partition, we must know where the partition starts, because it'll ask us for that address. If you put an address that's too early, it will overwrite the first partition. If you put an address that's too low, or too big rather, it will give you a gap between the two partitions. So you must make a careful note, copy and paste the value somewhere. Keep it safe. So the next thing we're going to do is we're going to use the D command, which is delete partition. Now at this point you might be thinking, whoa, I don't want to delete the partition. Nothing will happen until we apply the changes. And what we'll do, we're going to delete the partition, we're going to create a new partition with the same name, and it will simply resize the existing partition. So you can do this at any point, but I do recommend you do it before you install anything. So I press D, I want to delete the second partition, don't I? Get rid of that second partition. Okay, does that make sense? So I'm deleting the second partition. Then what I do, I need to create a new partition. So the command is n for new. Okay, it's pretty obvious. I want a primary partition. That's important. So I put P in, primary partition. I want to create the second partition. Yep, the one I've just deleted. So I put 2 in. And this is the value I memorised, or I copied off somewhere. That's my starting point. Yeah, if you get that wrong, you completely screw up your SD card. So it's really important that you copy and paste that value accurately. The last sector, I just press enter because the default value is the end of the SD card, and that's what I want. And then the last thing I do is I type in W, which stands for commit changes. Okay, no idea why that was W. And I think just see it gone. I type in W and I'm back to the command prompt. And I restart my server. It chucks away for a few minutes. And then you've got a big partition. So this is what I recommend you try this out before you go too far down the labs. You get this done early. So if you do make a mistake, you just have to reformat your SD card and start again. And now look, bang, look, 3.6 gig now in my, instead of 700 and something meg. So I can see it works by using the. Oh, sorry, when you restart, beg your pardon, one more command you have to type in. You have to resize to file system, and you have to tell it the second partition will then take over the space. Don't worry, I missed out on that the first time I did it. I couldn't work out why the partition was still small. That's the magic command. Resize to FS will do the final expansion of the file system. And that's it. You've now got the whole SD card being used for your server. Okay, I will very quickly take you through software because we've got time, which means you can get some software installed as part of the lab this week. Just about got enough time. We're going to use something called the Advanced Package tool. Okay, it's an interactive tool which allows you to install, delete new packages, new software on your system. It's like an app store for Linux. It's all command line. Now, what it does, there's a special file called etc app sources.list, and that contains the addresses of the archive, the addresses of where to find the packages. And you look something like this. Now look at the addresses. Okay. That says deb. That's the binary files. That's the source code. So you've got one archive which points to the pre-compiled applications, another archive which points to all the source code, so you can download the source code and recompile it yourself. Now, we are going to download all the application names that are available before we start. So when we search for applications, we can just search our local cache and see if the application exists. So the first thing you should always do is apt-get update, which downloads all the package names from the repository and stores them in a local file, a local cache. The second thing you should always do is upgrade what's already there. And that one command will upgrade every single piece of software on the Raspberry Pi. It can take a few minutes. It'll check for outdated versions, it will download the new versions, it will decompress them, it will install them, it will configure them, all with one command. So always upgrade what's installed. And if you want to install some software, we search for it in our cache. So if I want to install Tree, for instance, remember that graphical tool to show all the folders in the structure, I would say apt cache search Tree, and it would search my cache and display any packages which have the word tree in. So you can find what's available and you can then install it using apt-get install. And if you want to install 2 or 3 packages, you just keep chaining the package names. So you can install 10 packages at the same time in one line. And that will install the packages on your server. So installing packages is really easy. You know, you haven't got to compile stuff from source anymore. It's probably easier than Windows nowadays. If you want to remove a package, apt-get remove. And that will delete the package, any configuration files, It will always say, yes, are you sure? Just in case you got it wrong. We're going to uninstall these packages, are you sure? And you've got the option of dropping out at that point. Get remove allows you to remove packages. And a couple of useful packages, which are tree, which is the tree structure, so you can say tree and it displays all the subfolders in a nice structure. Sudo. We're going to talk about sudo next week. It allows an ordinary user to temporarily take on root permissions, root privileges, to install things. And Lix is a web browser for the command line, just for the sake of playing with it, see if it works, see what you think of it. It's a text-only web browser designed for the command line. Okay, just for curiosity's sake, I think you should install it and have a play with it, see if you can get it to work. The final bit to talk about is the manual. There is a full manual on the server. Every time you install a package, it installs the documentation for it as well, the help documentation. And I think it's really useful to know how to access that manual, isn't it? So if you get stuck with a command, you can find out how it works. So I'm going to show you how to use the manual. Because Linux users and Unix users are lazy people, in a non-sexist way, the command to access the manual is man. So if anyone in Linux talks about man, they're talking about the documentation. Okay, so it's a little bit tricky to get your head around some of these terms. Generally, most Linux commands are as short as they can possibly make them, because it's less typing. That's why you have to keep a record of how they work. So if I want to find out how the sudo command works, remember the one I've just installed? I type in man sudo. That's it. And it gives me pages of documentation with different headings. And the headings are always the same. You can find the different sections. To quit man, you type in :Q. To page down is Z, to page up is W. Now it sounds weird, but actually Z and W, if your hand's on the keyboard, they're like that. With your right hand. So without having to distort your fingers at all, you can access Z and W quite quickly. So you can page up and page down using Z and W. Because some keyboards don't have page up and page down keys. Mac users, I'm looking at you now. Yeah? There is no page up and page down. If you're lazy, you can use page up and page down. To search for something inside your manual, / and type what you're looking for. And it will find it in the manual, in the documentation for you. And if you want to keep toggling through the results, so if you search for something that comes up 10 times, you can keep pressing N for next, and it will cycle through all the places it's found it in. To go back up to the previous instance, it's Shift N. I've covered about 5% of the commands for manual, but that's probably enough to get you going. Next week, we're going to talk about access control, and we're going to talk about the Apache web server. And the two do kind of go hand in glove. Okay?